Hello, Assalamualaikum. How are you today? I hope you are doing fine. Before we start our presentation, you must know who are the presenters for today. First, Nur Najihah. Second, Nurin Firzanah, Nur Aziatul Akma, Nur Farahin, Siti Akmaliyana, Afrina Balqish, and the last one is Nurliyana. So, are you guys ready? The topic that we will discuss about today is telescopes as portal discovery. Hi, I'm Nur Najihah and I am the first presenter. I will explain to you briefly about telescope and the history of telescope. So, what is telescope? Telescope is a device used to form magnified images of distant objects. The telescope is undoubtedly the most important investigative tool in astronomy. It provides a means of collecting and analyzing radiation from celestial objects, even those in the far reach of the universe. Okay, moving on to the history of telescope. Hans Lippershey, the first person to patent a telescope in 1608. According to the legend, he conceived of the idea when seeing two children holding up two lenses that appeared to make a distant weather vane appear closer. Then, in 1609, Galileo Galilei heard about Hans' invention and invented his own telescope within days. Galileo was the first person to point a telescope skywards. He discovered the mountains and the craters on the moon, as well as the Milky Way, also discovered the rings of Saturn. Sir Isaac Newton later built the first reflecting telescopes in 1668. This is a type of telescope with a mirror in it rather than lenses. In 1789, William Herschel built the largest telescope of the 18th century in the UK. It was a giant reflector with a mirror that was 49 inches wide. Edwin Hubble used a 100-inch Hooker telescope to find variable stars in the Andromeda galaxy in 1924. This allowed him to scientifically derive that it was outside the Milky Way galaxy. Hubble has contributed so many discoveries to the whole world from then until today.
Assalamualaikum and hi everyone. My name is Nurin binti Mohamad Nasrodin. I am the next presenter. Alright, we move to the eyes and camera everyday light sensor. We will look what are the eyes, reflection, image formation, and focus light. Eyes are the organ of sight. The eye has a number of components. These components include but are not limited to the cornea, iris, pupils, lens, retina, macula, optic nerve, choroid, and vitreous. Next, we will look at the diagram of the eye. Number 1 is the iris. Iris is the color part of the eye that helps regulate the amount of light that enters the eye. Number 2, the pupil is the dark aperture in the iris that determines how much light is let into the eye. Right? Number 3, the cornea is the transparent part of the eyes that cover the front portion of the eye, and it also the clear front window of the eye that transmit and focus light into the eye. Number 4, the lens is the transparent structure inside the eye that focus light rays onto the retina. Number 5, the retina is the nerve layer that line the back of the eye, sense light, and create impulse that travel through the optic nerve to the brain. Then number 6, the macula is a small area in the retina that contains special light sensitive cell and allow us to see fine details clearly. Next, number 7 is the optic nerve. It is the nerve that connects the eye to the brain and carries the impulse formed by the retina to the visual cortex of the brain. Lastly, number 8, the vitreous. Vitreous is a clear and colorless fluid that fills the space between the lens and the retina of your eye. 99% of it consists of water and the rest is a mixture of collagen, proteins, salts, and sugars. Next, we will look at the lens focus light. The cornea and lens together focus a reduced inverted image of retina. The lens is composed of transparent, flexible tissue and is located directly behind the iris and the pupil. It is the second part of our eye after the cornea that helps to focus light and image on the retina. Besides this, behind the pupil lies the crystalline lens, which is responsible for focusing light. The lens can change its focal length like a camera. This is what allows you to focus close up on a book or far away at the horizon, but not both at the same time. To switch from one to the other, the lens actually bends and changes shape because of contraction in the ciliary muscle. Then, the back surface of the eye that consists of layer of cells whose function is to transmit to the brain information corresponding to the image formed on it. We will move to the refraction. Eye refraction is how the power of eyeglasses or contact lens is calculated. This measurement is based on how much the lens of the eye has to bend light rays to process visual stimuli. This is expressed in a measurement of distance and clarity. We see the world around us because of the way our eyes bend or refract light. Refractive error are optical imperfections that prevent the eye from properly focusing light and causing blur vision. Next is the example of refraction, which is refraction at the sunrise or sunset. Refraction can make the bottom part of the sun, which is near or even below the horizon, appear higher than it is. This can give the sun a distorted appearance that resembles an oval more than a sphere. Or sun will appear distorted at sunset because of how light bends in Earth's atmosphere. Because of our atmosphere, the light rays bend at sunrise and we see the sun early, although the sun is just below the horizon. Similarly, at the sunset, we see the apparent position of the sun due to the same bending of light rays, not the real position. We see the sun rising about 2 minutes before it is actually there because of refraction, and we see it for about 2 minutes more at sunset, even though it has already moved from that location.
Assalamualaikum and hi everyone. My name is Nur Aziatul Akma and now I'm going to present about camera. So how does a camera work? Do you know that a camera also can capture image similar to the way eye does? So how does a camera work? Camera produce picture by capturing or recording the characteristic of the lights from a scene or subject. A camera focus light captures the image with a detector. Digital cameras detect light with charged coupled device, which is CCDs. The CCD detected in the digital cameras are similar to those used in modern telescopes. Before we learn about the basics of how cameras work, let's get to know the main parts of the camera that are involved in the process of capturing picture or recording video. The main parts of camera is camera lens, focus ring, film, shutter release, shutter speed control, and aperture adjusting ring. Main part of camera is camera body. The camera body is a light-proof box. There are also located controls to exposure settings and others effects. Next is camera shutter. When the camera shutter release button is pressed, the camera shutters open and any light flowing into the camera lens is directed through the lens aperture and the open shutter to the camera image sensor. Shutter speed setting determines the amount of time the light is exposed. Next is the camera lens aperture. Camera lens aperture has similarity with eye. Aperture can be assumed as an eye for the camera. The amount light that reaches the image sensor is determined by size of the camera lens aperture opening that has been set. And last main part of the camera is memory card. When you take picture, the colors and characteristics of the light that the image sensor is exposed to is recorded by the image sensor and then saved to the camera memory card. The human eye and a camera are similar in the way they operate. Both capture the image using the same principles. Both also can focus the light and capture the image. So, this is comparison of similarities found in the working of the human eye and a camera. Cornea is the outer cover for eye, while lens is outer cover for a camera that has a transparent glass and sits in front of the camera body. Aperture is like an iris for camera. The aperture size refers to how much light is let into the camera. For an eye, retina is formed an image, while for the camera, image is formed over a film. And lastly, camera also has a hole through which light enter the lens, same as eye's pupil.
Hi, my name is Nur Farahin Hamzah, and I will present to you about telescopes and technology. So, first and foremost, what is invisible light and how to observe invisible light? As we know, the human eye can only see visible light, but light comes in many other colors like radio, infrared, ultraviolet, X-ray, and gamma ray that are invisible to the naked eye. On one end of the spectrum there is infrared light which, while too red for humans to see, is all around us and even emitted from our bodies. Warm-blooded animals, including humans, radiate infrared light. That's why infrared cameras are helpful for thermal imaging and night vision when searching for people or animals. Next, how to observe invisible light. As you can see in the picture, a standard satellite dish is essentially a telescope for observing radio waves. So the dish is the primary mirror reflecting radio wave toward the receiver. So the receiver acts like the secondary mirror, sending radio waves to a decoding device. There are too many types of telescope that can observe invisible light. For this light is radio telescopes. What is radio telescope? A radio telescope is like a giant mirror that reflects radio waves to a focus. Just as optical telescopes collect visible light, bring it to a focus, amplify it, and make it available for analysis by various instruments, so do radio telescopes collect weak radio light waves, bring it to a focus, amplify it, and make it available for analysis. They use radio telescopes to study naturally occurring radio light from stars, galaxies, black holes, and other astronomical objects. As you can see, the picture on the slide is Chandra X-ray Observatory. X-ray astronomy has its equivalent of the Hubble Space Telescopes in the Chandra X-ray Observatory. Chandra's mirrors are made of iridium and have an aperture of 10 meters, which is 33 feet. It can obtain high-resolution spectra and images of astronomical objects. The other type of telescope is infrared and ultraviolet telescopes. Infrared and ultraviolet light telescopes operate like visible light telescopes but need to be above the atmosphere to see all ultraviolet and UV wavelengths. So firstly, infrared telescopes is instrument designed to detect and resolve infrared radiation from sources outside Earth's atmosphere such as nebula, young stars, and gas and dust in other galaxies. Ultraviolet radiation comes from a hotter region of the electromagnetic spectrum than visible light. For example, interstellar gas at temperature close to 1 million kelvins is quite prominent in the ultraviolet. It has yielded much important information about chemical abundance and processes in the Sun and certain other stellar objects such as white dwarfs. Ultraviolet astronomy became visible with the advent of rockets capable of carrying instruments above Earth's atmosphere, which absorb most electromagnetic radiation of ultraviolet wavelengths, such as roughly 100 to 4,000 angstroms from celestial sources. As you can see in the picture, that is the example of infrared and ultraviolet telescopes, which is SOFIA and Spitzer. SOFIA stands for Stratospheric Observatory for Infrared Astronomy.
Assalamualaikum and hi everyone. My name is Siti Akmaliyana, binti Ahmad Sabri. I will explain to you guys about gamma ray telescopes and how can multiple telescopes work together. Other than the previous telescopes that have been explained, gamma ray telescopes also can be used to observe non-visible light. So, what is gamma ray telescope? Gamma ray telescope is one of the instruments designed to detect and resolve gamma rays from sources outside Earth's atmosphere. Do you guys know that different forms of light travel in waves of different length? This chart shows the different wavelengths of light. As you can see here, gamma rays all have wavelengths that are shorter than visible light. The shorter the wavelength, the more energy the radiation has. Gamma rays have the shortest wavelengths. So, they are the highest energy form of light. The gamma ray sky is spectacularly different from the one we perceive with our own eyes. That means gamma ray telescope must use sophisticated techniques that track the movement of individual gamma rays to construct an image. One technology that does this in use in the Fermi Gamma Ray Space Telescope, among other places, is called a pair production telescope. So this is the Fermi Gamma Ray Space Telescope. Fermi Gamma Ray Space Telescope is a NASA spacecraft. It is in space studying the most powerful sources of radiation in the universe. Are you guys wondering how does it work? Come on, let me explain more. So, Fermi uses a multi-layer sandwich of converter and detector materials. When a gamma ray enters the front of the detector, it hits a converter layer made of dense material such as lead, which causes the gamma ray to produce an electron and a positron. The electron and positron then continue to traverse the telescope, passing through layers of detector material. These layers track the movement of each particle by recording slight bursts of electrical charge along the layer. This trail of bursts allows astronomers to reconstruct the energy and direction of the original gamma ray. Tracing back along that path points to the source of the ray out in space. This data can then be used to create an image. Next, how can multiple telescopes work together? Is it possible for multiple telescopes work together? Definitely yes. There is a powerful technique for linking more telescopes, known as interferometry. With interferometry, radio astronomers can combine the signals from many antennas and even many telescopes. It allows them to create an image that is much brighter and sharper than what is possible from a single antenna dish. Interferometers are used to increase the resolving power of a telescope, and VLA or Very Large Array is one of the interferometers. Before I finish my presentation for today, I would like to explain a little bit about the Very Large Array, VLA. The VLA is an interferometer made up of 27 radio telescopes arranged in the shape of a Y. Each dish is 82 feet across and weighs 230 tons. The spacing between the dishes can be changed to allow different types of observations to take place. The farther apart the dishes are, the better the telescope's resolution to distinguish between two close objects. When the dishes are closer together, the resolution is less, but the telescope can get more information about characteristics such as the object's brightness and temperature.
Assalamualaikum warahmatullahi wabarakatuh. My name is Afrina Balqish. I'm with my friend Nurliyana binti Fariz Ezwa. Today we would like to share about the basic of handling telescope. In this basic of handling telescope, we got three parts. The first part is getting a telescope. Okay, for the first part, we need to consider the type of telescope. Different telescope got better different types of viewing. So basically, there is three types of telescope: refractor, and catadioptric. For the refractor, it has a long thin tube with an objective lens at the front that collects and focuses the light. For the reflector, employs a large concave mirror rather than a lens for the purpose of accumulating and focusing light. For the last one, the catadioptric, it is a compound telescope, combining both lenses and mirrors. They are good photographic telescope and they are a lot easier to carry than the reflector. So, the most easy one and better is the catadioptric. Next, we need to consider where you live. You need different power levels considering where you are. If you have an area where the light pollution is better or worse, if you are in an area where it rains more. For example, if you want to do a bird watch, you can't use the reflector telescope because it won't show you terrestrial object. After that, if you want to see the night, you need to use refractor or cardioptric telescope. It might be your best option. The last part one is you need to consider what you want to look at. For example, you need to see the objects like the planets, the moon, and closer star need a high power, good contrast, and sharp resolution in a telescope. So, if this is what you want to look at, your best bet is to go with a refractor or a reflector. If you are looking at faint objects such as galaxies and nebulae, you need a bigger aperture and choose a big reflector telescope. For the part 2, I will explain to understanding your telescope. Firstly, in understanding your telescope, you need to learn the finder scope. This is typically attached the side of the telescope. It displays more of the sky than the scope itself. For instance, a 50 power telescope covers an area about as small as the fingernail on your little finger, whereas an 8 times finder scope covers an area about the size of a golf ball. Next, you need to learn the mount. So basically, telescopes come in two types, equatorial or altazimuth. You need to know which kind of telescope you have so you can learn how to operate your telescope. So, what is altazimuth? Altazimuth mount operates by going up and down and side to side, making it easier for beginners to operate. So, what is equatorial mount? Equatorial mount swing across the celestials north to south and east to west. The polar axis needs to be aligned to Polaris, the North Star. So the last one for part 2 is you need to learn the tripod. You need to make sure the three legs of your tripod are properly balanced, otherwise the telescope will fall over and become damaged. When you're scouting a location, always look for areas that have a flat, level area for your telescope.
Assalamualaikum, I'm Nurliyana as Afrina's partner, so today I will continue the part 3, which is scanning the sky. Okay, as for scanning the sky, there are a few important steps that you need to know. As for the first one, it is learn the sky. Before you start tromping around in the dark with your expensive telescope, you will need to figure out what you are looking for first. Maybe some of you want to have a gander at the moon or want to check out the planets, and maybe some of you are interested in a meteor shower. Whatever it is, first of all, you need to find out the timing, place, and weather. Basically, if you are trying to observe the stars just like that, for instance like going out on a moonlit night won't get you very far. First of all, you have to look at the books on stars and constellations so that you will gain knowledge from them, and all the books will tell you when the best viewing times are and when the planets are easiest to be seen. It will help you a lot. As for the third tips, you have to examine your sky chart first so that when you are out in the dark, you know where to point your telescope. Okay, the last one is you have to train your eyes. To do so, you have to make sketches of the moon or planets or whatever sketch that you want to sketch, because it will help you to look more closely at the sky and observe the details. Okay, the second step in scanning the sky is choose your spot. You have to choose your spot carefully. Once you have decided what you are looking for and where it will be, you will need to be accessible at night and have a place with solid level ground for your telescope's tripod. Okay, as for choosing your spot, it has few things that you should take into account when you are handling your telescope, which is the first one, you will need to consider the light pollution. For example, if you are in a big city going up on a high roof, as long as it is safe, it can get you away from the worst of the light pollution and allows you to see more clearly. Next, you also have to try to avoid decks and blacktop driveways and concrete at all costs. It is because it may lead you to the bad consequences. For example, footsteps on a deck may cause vibrations in the image, and blacktops, driveways, and concrete can create thermal issues for your telescope. The next step is practice. As you know, before we start doing everything, we have to practice first so that it will go smoothly. Same goes to scanning the sky. You will need to practice setting up your telescope and pointing to the correct part of the sky before you start fiddling around at night. Or otherwise, it is very easy to lose bits of your telescope and forget how to do something. Okay, here's a suggestion. For practice, you can set up your telescope and using the lowest power eyepiece, and point the main scope at something about 100 feet away like a tree. And then center the object in your crosshairs and make sure it is clear. And then you can switch to a higher powered eyepiece and try it again. Okay, as for the last steps of scanning the sky is you have to be comfortable. Before you start completing your desire to see the star above the sky, you have to make sure that when you are having your big night out with the stars, that you have dressed appropriately and comfortably first. If it is going to be cool, make sure you have the right clothes on and bring along a canister of something warm.
I have a question. Do you love stargazing? Or is there anyone around you loves stargazing? Yes, most of us love stargazing, right? Obviously, at the night sky. The next time you gaze up at the night sky, you are likely to spot a twinkling star. But is it really twinkling? What looks like a twinkling star to our eyes is actually steady starlight that has been distorted or bent by the Earth's atmosphere. The visual effect of this distortion is like looking at an object through a glass of water. Telescopes here on the ground, which also must peer through Earth's atmosphere, are equally vulnerable to our atmosphere's visual tricks. That's why astronomers around the world dream of having an observatory in space. From a position above Earth's atmosphere, a telescope would be able to detect light from stars, galaxies, and other objects in space before that light is absorbed or distorted. Therefore, the view would be a lot sharper than that from even the largest telescope on the ground. So, do their dreams come true? In the 1970s, the European Space Agency and the National Aeronautics and Space Administration (NASA) began working together to design and build what would become the Hubble Space Telescope. On April 25, 1990, 5 astronauts aboard the Space Shuttle Discovery deployed the eagerly anticipated telescope in an orbit roughly 380 miles, equal to 600 kilometers, above the Earth's surface. That deployment and, later, the unprecedented images that Hubble delivered represented the fulfillment of a 50-year dream and more than 2 decades of dedicated collaboration between scientists, engineers, contractors, and institutions from all over the world. To end our presentation, you will see some of the images captured beautifully by the Hubble Space Telescope. Until then, thank you for watching. Assalamualaikum.